G'day chemists. So let's have a look at some examination feedback. So this is an exam that my students have done. It's based on past IB questions for paper 1A and 1B. So this is basically a walk through the paper, how to do each question. It's the SL and HL paper. I've sort of formatted it so that the questions 1 to 15 in the part 1A are multiple choice SL, and then 16 to 25 are multiple choice HL, and then there are specific HL questions in part B, which will stand out. Okay, so let's get into it. All right, question 1. What is the mass number of an isotope of carbon with 6 protons and 8 neutrons? So first off, this is our carbon atom. That's from the periodic table, obviously. These are the key words in this one. Like, there's some fun things to pull out, and we'll sort of go through these as we do it. We can just give you the answers, but we're looking to sort of go through each of these questions in the most thorough way possible to make sure that, our students and anyone else who's watching this are able to understand it. The paper that those students did will be there'll be a link to that in the comments below. Okay, so what is the mass number of an isotope of carbon with 6 protons, 8 neutrons? We have the answers are A, 6, B, 8, C, 12, and D, 14. Okay, so first off, we know it's not 6, right? Like, that's the number of protons. So we know that one proton has an atomic mass of 1, there enough, and one neutron has an atomic mass of 1 neutron. So this would only take into account the protons. And this would only take into account the 8 neutrons. It ignores the protons altogether. So we know it's not those. But we also know that if we go to 6 protons plus 8 neutrons, that gives us 14. So the answer is not carbon 12, not C12. It is D14, the tope. Alrighty. So question 2, which statement correctly explains the increasing first ionization energy across period 2? Alrighty. First off, this is the period we're talking about, period 2. Remember, periods, not portraits. That came from a former student of mine, and it really sticks in my brain. Periods aren't portraits, so, it's landscape. It works. First, let's look at our options. So let's look at our options. Which statement correctly explains the increasing first ionization energy across period 2? A nuclear charge decreases and shielding increases. Alright. Nuclear charge increases while shielding remains the same, or remains similar. Shielding increases more than nuclear charge, and atomic radius increases across the period. Alrighty, first off, more protons equals a higher nuclear charge. Therefore, it increases, right? So the more we go across, we have a new proton each time we move across one. Therefore, the nuclear charge increases. So it is not going to be A, because that says nuclear charge decreases. So as those numbers of protons increase, the atomic radius decreases, and that's because the number of protons sort of pull the electrons. And remember, across the period, they've only got the same number of shells. Pulls the electrons closer because the charge has gone up, right? So as that charge goes up, the more positive, so the negative electrons get pulled tighter. So as there are more protons, the atomic radius decreases, and that means it's not D. We also know that shielding is due to the amount of interior electrons. This is actually constant across the period. Like, for example, lithium here has 2 internal electrons and 1 valence electrons. Beryllium has 2 internal electrons and 2 valence electrons, but it's the interior electrons that cause shielding, so that's pretty constant across the thing. So the shielding does not increase more than the nuclear charge. In fact, the nuclear charge increases while shielding remains fairly similar. Alright, next question. So which of the following elements has the highest first ionization energy? It could be neon, so neon is right here. It could be aluminium, which is there. Could be magnesium. And it could be sodium. So highest first ionization energy. This is a different question to the one previously. Related though. We're testing different aspects of the understanding. So first we're looking to see if we recognize the trend. As we move left to right, the first ionization energy increases. As we move bottom to top, using our periods, it increases. So it increases left to right, increases bottom to top as using the periods and the groups respectively, and that means it has to be neon because neon is in this corner as we go up and across. All right, so electron configuration. What is the electron configuration of a neutral atom of nitrogen? So nitrogen is right here. Neutral means that it is, first off, it's in the P block. It's in group 2P. And that makes sense, right? Like, so all of these are 1s2, 2s1, or 1s, 2s, 2p. Like, they all fit that format. So there are 7 electrons, all right? And that means that takes out A and B straight away, because A and C, because we've got 2, 3, 8, 2, 4, 10 electrons. So those are out straight away. And when we use Aufbau, that means it fills the lowest energy levels or shells. The lowest energy shells fill up first. So here in B, you'll notice we have a 2s1, and over here we have a 2s2. So these both have 7 electrons, but here the lower energy is not filled up first. So that should be 2s2, and here the lowest energy is filled up first. 2p3. So 1s2, 2s2, 2p3 is our correct answer. And it's actually a really easy way to do that as well. So you know that that's 1s, right? That's full. We know that 2s is full because of this. And here we're in the 2p block. It's a neutral atom, so it's got all its regular electrons. So we just go 2s, 2p1, 2p2, 2p3. And that's that. So I've jumped ahead and given you the answer here already. Which statement best explains why graphite conducts electricity? The answer is A, it has delocalized electrons. It does not contain metal atoms because it looks like this, right? It does not contain metal atoms because it's all carbon. Carbons are not metal. It does not contain polar covalent bonds because the difference between these two is the same, like 0. So it's not polar. And it does not have free ions. It does have this delocalized sea of electrons. So carbon is this large covalent structure, and it has these 3 localized electron bonds around the carbon. Graphite is this large structure, sorry. It has this 1 delocalized electron right here, and that's for each carbon. And that's able to move through that zone there, which gives it the ability to conduct electricity. All right, so what is the empirical formula of a compound with 40% carbon, 6.7% hydrogen, and 53% oxygen by mass? The easiest way to do this is to choose one element. I like oxygen. It's the one that jumps out at me all the time as 16.00. I know you've got 1.008. I know you've got 12.00 like there, or 12.01. But see, that's what I mean, like depending on your periodic table, for me, 16.00, that's the one I'm going to go with. So the first step is to work out what the molar mass or molecular mass of each of these molecules is. For that, we need the periodic table. So 12.01, 16.00, 1.01, that's our IB periodic table. And here they are. So we've got 32.02 grams per mole, 44.04 grams per mole, 32.04 grams per mole, and 46.06 grams per mole. Sweet as, not a problem. So we'll start with A, and then we'll look at the percentage of oxygen, because because they're all different, right? Like if you find out one of them, it's all going to sort of fall into line after that. So 16.00 divided by 30.02 times 100 gives us 53.3% for A. All right, so already we've found the correct answer. Let's dip through the rest just to check. 16 divided by 44.04 gives us about 36%. So B is not the answer. C, we're hitting a 49.9%, so that's incorrect. That's the closest one. And D, we're hitting 34.7%. But that's just the process, right? We take the mass, we divide it by the total mass, molecular mass, and then multiply it by 100. That gets us our percentages. And we could do that for each element, and it would all work out. But A, bang, because of oxygen. All right, so this question, we're going to look at which molecule has the trigonal, or trigonal, we say trigonal in class for fun, pyramidal shape. We have CO2, BF3, NH3, or CH4. So trigonal pyramidal shape. Let's have a quick look at the way I would do this. I would always do this by drawing it. It's not the only way to do it. There is a wonderful table that you can remember. Looks at electron domains and bonding domains and whatnot. So let's draw them out. First off, carbon dioxide, we have this wonderful linear molecule, so it's not going to be that one. Then we have a trigonal planar molecule right here, with the boron in the middle and the fluorides off the top there, or fluorines off the top, sorry. But that's like a flat molecule, so it's not BF3. Then we skipped one, see, tetrahedral methane there. So methane has this like boom, boom, boom. It has 4 electron domains and 4 bonding pairs, okay, and that gives us the tetrahedral shape. So it's not that one. But ammonia has 4 electron domains, but 3 bonding electron pairs. And that gives us the trigonal pyramidal shape. It's a good one. I like that one. So the answer is C. All right, what is the molar mass of calcium nitrate? Ca brackets NO3 brackets 2. We have A, 102 grams per mole. We have B, 164 grams per mole, 62 grams per mole, or 118 grams per mole. These are the periodic tiles. Look, there's only one way to do it, and that's to add them up. But there is a little point where people are going to get caught out, and that is this 2 here. So the question is actually testing, do you understand how molar mass works? But B, do you understand what this 2 means in a chemical formula? Which is this NO3 here is doubled. So there's 1 calcium, 2 nitrogens, 6 oxygens. And so let's draw it out, right? So we go 4.08, 40.08 plus, in brackets or parentheses, 14.01 plus 16.00 times 3, close parentheses, times 2, gives us 164 grams per mole. B is our correct answer. All right, so which element has the electron configuration argon, 4s2, 3d10, 4p5? And our options are bromine, krypton, selenium, and arsenic. So let's have a look. Or is that astatine? I'm not sure off the top of my head. I can't remember. It's been a long day. Alrighty. So let's, just for fun, let's break our periodic table up into blocks, because this will come into it at different points, right? So this is our S block, this is our D block, and this is our P block. Transition out metals just to make things fun. So let's have a look. We know it's not krypton, because krypton's a noble gas, so it would just be compressed as brackets Kr if we were going to do that, right? Like that's not how it would work. But we're in this 4p group here, right? So all of these are in, are they all in the 4p? Selenium, yeah, they're all in the 4p group here, right? So from here, we know that 3d10 is filled, because that's that one there. Yeah. We know the 4s2 is filled, because that's there. So 4p, we go 1, 2, 3, 4, 5. It's 5 up here. That gets us to bromine. So that's going to be our correct answer. Alrighty. What is the enthalpy change in kilojoules of the following reaction? We have 3H2 plus, so we're back to the, what's it called? The Born-Haber question. Not Born-Haber. We're back to the Haber cycle equation. So if 3H2 plus N2 goes to 2NH3. So straight up, this is our answer. Alrighty. So our bond enthalpies are bonds broken, sum of bonds broken, minus sum of bonds formed. And I'll show you how we got to this answer down here. So this is our reactants minus the sums of the bonds of the products. The easiest way to do this is always to draw them, right? So we have 3 of these HH bonds, right, in the H2s, because that's just HH, plus 1 of these N triple bonds. That's over here for N2. Then we have 2 of this molecule here. All right. Now that 2 of those molecules actually means there are 3 of the NH bonds times 2. So it becomes 3 times HH plus NN minus, because those are our bonds that are broken, minus 2 times 3 times the NH. So if we write that out, it becomes this, right? 3 times 436, because that's this bond up here. 945 is the energy in this bond. It's pretty energetic bond there, that triple. Makes sense. Minus 6 times 391. So 2 times 3 gets you to 6. And 391 is that. And that is D. Those are all of our SL questions. The remaining 10 questions after this are HL questions, HL multiple choice questions. And so yeah, so if that's you, stick around. Otherwise, skip forward a little bit. Who doesn't love a Maxwell-Boltzmann diagram? Okay, so the following diagram, which best describes the relationship between temperature 1, that's this one here, and temperature 2. Alrighty, let's have a look. So, one of the things we know is that as temperature goes up, the average kinetic energy goes up. So here, the average kinetic energy has increased, right? Like you see, this axis here is kinetic energy. So the average is further along. So that means temperature 1 is cooler than temperature 2. Therefore, T2 is greater than T1. And the answer is C. So which expression correctly applies Hess's law? So we have delta H equals delta H F products minus delta H F reactants. We have bonds broken minus bonds formed. We have sum of the enthalpy of the products divided by the sum of the enthalpy of the reactants. And then we have the enthalpy of vaporization minus the enthalpy of formation. So Hess's law is cycles, right? And it's always this. So we have the change of reactants, right, going on. So this is what we're looking for, delta H going that way, which means it's delta H plus reactants gives you delta H products. So if we cycle that around, for Hess's law, we can have delta H products minus delta H reactants. This is a tricky one because this is one that we use when we use bond enthalpies. But this one here is, again, our Hess's law version of enthalpy. So yeah, A is the answer. Alright. Meow. Just put me over there. Okay, so consider the two reactions involving iron and oxygen. We have 2 Fe plus 2 oxygen molecules gives you a Fe ferrous oxide salt. 2 of those at minus, so it's an exothermic at minus 544 kilojoules. Over here we have 4 ions, goes to plus 3 oxygen, goes to 2 ferrous oxides, and see how they are different. That means they are different transition states of iron, and this gives us a negative 1648. So what you'll notice is that these are the enthalpies of formation, like these are the formation reactions for this right here, which is our target equation, 4 FeO plus 2 F2O3. Notice that is a 2, there's a 4, there's some doubling along the way. Let's have a look at how we actually do it. So we're in Hess's, so these are enthalpies of formation. So we're going to use a Hess cycle, and I think cycles are the best way to do it. So we write our target equation, okay? We write our formation elements down here. Here, remember, going up to FeO, so it's negative 544, which we get from right there. But don't forget that 2 at the front there, but it needs to be a 4, so we have to double it. Then 0. Then we go up here, minus 1648. We don't need to do anything because that 2 is the same as that 2 there. Now for funds, this is our target reaction. This is why the cycles are such a good way of doing it, because you can see that these are going in one direction, this is going the other way. So those are on opposite sides of our equation. So we have x, which is that one, plus 2 times negative 544 equals negative 1648. And then we just like swap them around. And that's our answer over here. This one here is a point of confusion, right? So A is our answer. So this one here is a point of confusion because often when we move this over, what we have to reverse is the operator, not the numbers here. And people get confused by that, right? Like, because it looks like the minus is going out the front. But that's an operation. That's not a sign of the direction that energy is traveling. Okay, fun. Alrighty. So, which condition favors the following exothermic equilibrium process? So it's telling you, this is the Haber process. You're going to see this a couple of times in the exam. It's something that I wanted to focus on with my class to make sure, to really tease apart where they understood it, where they didn't. So following exothermic process. So this process is exothermic going in this direction. That's why it is written that way. It's an equilibrium process. So let's have a look. If we remove reactants, that will take these away and will drive the reaction backwards, meaning it will favor the endothermic process. Okay, so it'll try and replace these ones. So it'll use up all of this and become more endothermic, not favoring the exothermic process. So it's not that. Add a catalyst, just happens faster, no change in position. Alright, if we increase the temperature, so as the temperature goes up, it's going to favor the endothermic system because, Le Chatelier says that if we make a change in the system, the system will try and reverse that change or minimize that change. So as the temperature goes up, it's going to favor the endothermic, so that's going to go in the other direction, which means if we increase the pressure, because there's 4 molecules and 2 molecules on this side, as we increase the pressure, we're going to drive it towards the exothermic side, which means we'll be favoring the exothermic process. Which compound has the highest boiling point? Fun! Okay, I'd like to do this by drawing them, because we're going to be talking about intermolecular forces. Okay, so first off, here we have methane, and here we have carbon dioxide. They have London dispersion forces, no other intermolecular forces going on there, right? So it's not those ones. They're really these bad boys. These bad boys have hydrogen bonding, which is strong, okay? And we can see that, like here we have, if we redraw it, you don't have to draw it, you can just work this out, but I'm doing it to show you. So between these hydrogens and oxygens, we'll have hydrogen bonding, and we'll have hydrogen bonding between these nitrogens and hydrogens right there. Okay, so what does that mean? That means it's going to have a higher boiling point. Both of them will have higher boiling points than these two. But now we need to work out which one has the highest boiling point out of these two. So the electronegative difference between H and O is stronger than H and N. Therefore, water has stronger hydrogen bonding between the molecules, so it will have a higher boiling point. So C is the answer. Alright, so let's have a look at our HL questions. What is the relative atomic mass of an element with the following mass spectrum? We have a stack of about 80% of them here on 23, 20% on 28, and our answers are potential answers. They call them distractors, which I don't love. Potential answers are 24, 25, 26, and 27. So let's have a look at how we're going to do this. First, relative atomic mass equals the sum of the mass times abundance divided by total abundance. That total abundance is, if we add up all the percentages, what that adds up to. So that's going to be 100. So we have 23 at 80 and 28 at 20. Lots of different ways around this. There's actually 2 different ways to do this equation. So first off, we could go 23 times 80 plus 28 times 20 divided by 100. Or, because it's percentages, you could go 23 times 0.8 plus 28 times 0.2, get rid of this 100. And either way, you get 24, which means the answer is A, 24. So here's a second ionization energy or successive ionization energies question. So 17, the values or successive ionization energies for an element are shown in the table below. First ionization energy is 420, then 3600, then 4400, then 5900. Oh, that feels gross. 5900, 4400, 3600. I just needed to correct that. My brain was hurting. Which group would you expect to find this element? So, first things first. Large order of magnitude jumps occur as you remove a complete shell. So once you get rid of a full shell, you're now hitting a huge jump to sort of start pulling away because you're closer to the nucleus. So the jump here is between electron 1 and 2, so first and second, which means this is in the first group. And we know it's at least this one here, right? Because if it was this one, you would only have 2 more electron energies, ionization energies. If it was this one, you would have no more ionization energies. So it's only from like here onwards, all of a sudden you go, now we have more to remove. Yeah, anyway, no, heroes, sorry. We have more to remove. Fun times, which means there has to be 1. Okay, next one. Which reaction has the greatest increase in entropy? Entropy is disorder or chaos, so which ones of these has the greatest increase in chaos? First off, this one has 3 gases going to 2 liquids and solids. That's less chaos, so that's not it. This one here has a solid and a gas going to a solid, way less chaotic. So B's out. We skipped C. So D has 2 gas to 2 gas. So any change in delta S is going to be very, very small. In fact, this is actually slightly less chaotic because we're bonding these guys together. Then we have solid plus a liquid goes to solid and gas. That's more chaotic, greatest increase in entropy. The answer is C. So then let's have a look. What is the abbreviated electron configuration of the telluride ion? Te2-. Well, obviously we're going to need our periodic table, but we also go Krs, they're all Krs, 5s2s, they're all 5s2s, 5d10, 5p6, 4d10, 5p2, 4d10, 5p4, 4d10, 5p5. So we're testing something here. So your telluride is over here. The first thing we're testing is that this 5p in the 5p block, it should go to 4, okay, but that's for the neutral atom. So telluride itself is 5s2, 4d10, 5p4. It's tricky. Sometimes we'll look at this one because we know that this is like 5p, right? Sometimes a student will go, well, that means this one's 5d, but that's 4d. Okay, so that takes, well, first off, let's have a look at this. A neutral atom is that. It's an ion, so we know that one's out, okay? Then, as I was saying, the 4d10, we know it can't be that one, so that one's gone. See you later, pal. And then it's a -2, which means it has gained 2 electrons, not lost 2 electrons. So, as it has 2 extra things, it's more negative. It can't be this because this has lost electrons, and it has to be this because it's gained electrons. So that's D. Kr, 5s2, 4d10, 5p6. Now, in my experience in teaching IB chemistry, I think I'd say, and even HSC chemistry, I think I'd say the periodic, the electron configurations, complexes, anything involving transition metals seems to be the biggest hassles. Like they seem to be the ones that students struggle with the most. So let's go through this step by step. What is the correct electron configuration for the Cu+, that's copper 1, ion? We have Ar, okay, so argon, and then all the way across here, 3d9, 4s1, 3d7, 4s2, 3d10, 3d8, 4s1. That's weird, isn't it? This D here, 3D, is after the 4S in all of them. And that's correct. That's because the 4S one is more energetic than the 3D. So it sort of fills up. Then the 4S is more energetic than the 3D. So it fills up first. Okay. Let's have a look. So copper is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Oop, I did a bit of a whoopsie. First off, 4s1, 3d10. Let's swap around a minute. Just stick with us. It's more energetically stable to have a full or half full, so d10 or d5 shell, if it's possible, right? So that is obviously going to impact this. So we've gone from 2 to 9, right? 1 to 10. And that's the thing with transition metals. Often they have these like partially filled S shells. Okay, so we switch these around when we write them, okay? So it becomes argon, 3d10, 4s1. That's copper. That's copper as copper stands. Alrighty. So We know it's not 3d7 4s2 because that shell is not filled up first. But the Cu plus has lost an electron. Okay, so we know this one here is 2 electrons down, right? So it's not D. And this one, the 4s ionizes before the 3D, because again, this 3d10 is more energetically stable. So that means it's not this one. This one's gone from 3d10 to 3d9. So that's the wrong order of ionization, which means it's 3d10. That is our Cu plus electron configuration. So this is a nice fun question. How many bonding electrons are there in the urea molecule? Here it is here. And there's so many places to go wrong. It's fun though. So it's simple, it's straightforward, but there's some tricky bits to it. So we could look at this molecule and be like, sick, that's it. 1, 2, 3, 4. And each one of these is a pair of electrons, right? So they go 8, bang, done. But I find it best if we draw it out in an expanded format where we have every electron shown. I like to in like atoms that are adjacent to each other, alternate between crosses and dots. We draw a bit more circly than dots when we draw it on the screen. But anyway, crosses and dots, so you can see which electrons belong to which atom. Now, if we highlight all of our bonding pairs, right, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8. 8 bonding pairs. Fun. That's awesome. That means there's 16 electrons, so it's going to be that. But there's also, so there's 8, but then there's like bonding pair, non-bonding pair. So 8, 9, 10. And that could get us to, so because everyone knows that oxygen has that there, right? Everyone understands the oxygen has 2 there. So that could get us to 20, which would be an easy mistake to make if we were just counting up all the bondings. But then that's assuming we don't understand how nitrogen works, which is pretty common actually. So then some people might go, well, there's this one here, this one here. That gets us 24. But remember, only looking for bonding pairs. So that keeps us at 16. So a lattice enthalpy question, a genuine Bornhaber question, I guess. So which equation represents the lattice enthalpy of magnesium sulfide? The first thing we need to know is that it involves gaseous ions. So A and D are, A and D are out because we don't have ions and they're not gases. Okay, so not ions here, not gases there. Next is that magnesium goes to 2+. Sulfur goes to 2-, which makes it C. C is the correct answer. Here we have the combustion for glucose as an exothermic reaction. The combustion of glucose is exothermic and occurs according to the following equation. Glucose plus oxygen goes to carbon dioxide plus water, water vapor. Which is correct for this reaction? Okay, first off, it's exothermic, so we know that this is negative. Then the change in entropy, it's going from a solid to all gases, so it's a positive change. It's getting more entropic. Now, whether or not that makes it spontaneous is a tricky one. I always try, it's not really, but the trick I use is I always try and remember this table, negative, so those two are out. I always try and remember this table, okay? So if we have a delta H is positive and we've got a negative entropy, it's non-spontaneous. If your delta H is negative and a positive entropy, it is spontaneous. And then we get involved in the low temperatures, high temperatures. But for us, we're looking at a negative enthalpy, positive entropy. Therefore, we're going to have a spontaneous reaction. And our answer is A. Which molecule has a non-bonding lone pair of electrons on the central atom? I've already given you the answer. The way we work this one out is, as usual, by drawing it. So if you draw our 4 molecules, right? We've got BF3, we've got SO2, we've got carbon dioxide, we've got silicon, that's wrong, SiF2, and it should be Si, not S. Anyway, so if we have a look, this is our only single this is our only single lone bonding pair, non-bonding pair, around the central atom, so it's going to be B. All right, the rate expression for a reaction is rate equals K brackets X, or square brackets X, square brackets Y. Which statement is correct? First off, as the temperature increases, the rate constant decreases. The rate constant increases with increased temperature, but eventually reaches a constant value. As the temperature increases, the rate constant increases. And the rate constant is not affected by a change in temperature. First off, we know that K is always temperature dependent. D, you're gone. We also know that as the temperature goes up, the rate goes up, and it doesn't reach a constant value. So that means A and B are out, and C is the correct answer. As temperature increases, the rate constant increases. All right, those are our multiple choice questions. We'll now jump into our sort of... Okay, so let's have a look at our first short answer response questions. I guess extended response too, really, as they move through. But this is modeled on part B of paper 1. Okay, so let's first look at our balancing equation question. Balancing equation below, Na plus F2 goes to NaF. Alrighty, so the very first thing you want to do when you do a balancing equation is, at our school, we call this the ERP table. That was given to me by one of my students. And we have the elements, the reactant side, the product side. Now you should do this each time this comes up, right? I'm not going to. I'm going to do it this once, and then it's a method you can go through. Okay, so on the reactant side, we have 1 sodium, 2 fluorine atoms. On the product side, we have 1 sodium, 1 fluorine, actually, 1, 1, 1, 1. First thing you do is you want to balance the metals. The metals are balanced, sodium. Then you balance the non-metals. So we'll put a 2 out in front of that sodium fluoride. And now we have 2 fluorines on either side. But we also have now 2 sodiums on the product side. So we need to balance that by putting a 2 out in front of the sodium, gold, and then we need to write our answer. This is just working, by the way. Don't, in the exam, do this and think you've answered it. This is just the working. So 2 sodium solid plus fluorine to gas gives 2 sodium fluorides. All right. So now we want to determine which one of magnesium oxide and sodium fluoride has a larger lattice enthalpy, and we want to explain why. So lattice enthalpy and explain, that's our key terms here. So first, we get 1 point for identifying, right? Magnesium oxide has the higher lattice enthalpy, and then we get a point for explaining it. So larger difference in ionic charge, +2 to 2 minus, versus +1 to 1 negative. And or we could talk about the smaller ionic radius, or radii between the two. Therefore, this leads to a stronger electrostatic attraction. So we have what is happening, this bit here, and the impact of what is happening. That's an explanation, okay? So if you're asked to explain, identify what is happening, then what are the implications of that thing that's happening are. Okay, write a balanced equation for the combustion reaction between magnesium and oxygen to give you magnesium oxide. We don't need to sort of show this because it gives it to us here, but it's just an interesting point where we can just make sure that we understand how ionic bonding works for you, not for answering the question. So if we've got magnesium 2 plus and then 2 minus there, we do a little swap and drop. Yeah, that goes down there, that goes down there. You know, Mg2O2. But ionic solids are ratios, so that therefore gets cut down to MgO. Okay, so here's our equation. Mg plus O2 goes to MgO. Straightforward. Balancing, not so tricky. 2 and 2. And that's our balancing. Again, we didn't do the ERP table. This question's again, it's very similar to that one. I just wanted to make sure with our students, we've been finding, sometimes combustion can be when moving between organics or inorganics, and I just wanted to make sure they sort of had that down when we're talking about combustion there. Okay, so name and explain the type of bonding between magnesium and oxygen to make magnesium oxide. All right, so name and explain. So one for naming, one for explaining. Naming it, explaining the electron transfer and electrostatic attraction between ions. Okay, so we have ionic bonding. Magnesium loses 2 electrons, oxygen gains the 2 electron, forming Mg2 plus and O2 minus ions. Oppositely charged ions are held together in fixed ratios by strong electrostatic forces. What is happening? Naming what is happening and explaining the impact of what is happening. All right, so as I talked about, there's, we've had students with that sort of struggling in combustion. So now I've got the other question to sort of see where they're going, how they're understanding some organic combustion or covalent combustion either way, but organics in particular. So we're going to write the balanced equation for the combustion of, what's that going to be? That's going to be propane, C3H8. It's organic. Therefore, your products are going to be carbon dioxide and water, or H2O, as a gas because it's hot. So here's our initial one, right? So when anything's combusting, it's being added to oxygen. Oxygen is being added to it. So C3H8 plus O2 goes to H2O plus CO2. Complete combustion. We do an ERP table. We're going to keep moving on though. Otherwise, we'll be here forever. And there are no metals to balance, so we balance the carbon, then the oxygen, hydrogen, and we see that we have 3 carbons, right? That makes sense. That gives us now 6 over here, and we have 8 hydrogens, so we have to times this one by 4. So we've got 6 plus 4, that gives us 10, so that makes that 5O2. Alrighty, I'm going to move myself over here. Yoink. Okay. So now, as we continue, explain the difference between the boiling and melting points of water and carbon dioxide in terms of their intermolecular bonding. Okay, so first we want to identify intermolecular bonding types within carbon and dioxide and water. That's our first mark, and then we want to relate it to melting point or boiling point. It probably should be melting point and boiling point. I'd actually say this question could be better written, and I would make it melting or boiling points, either one. Okay, so H2O forms hydrogen bonds between molecules while CO2 forms London dispersion forces. Perfect. And then H bonds are stronger than LDF, leading to a higher melting point for H2O. So that's how we would roll with that one. This is what happens. Also, this is the identification. Here we have what's happening. Here is the implication. Explaining. This is also something we've been working on in class. That's why there's a lot of explain questions. All right, one of my favorites, Lewis diagrams. So in the boxes below, please draw Lewis diagrams for CO2 and sodium fluoride. Okay, nice and straightforward. We have 8 electrons around our oxygen, 8 around our carbon, 8 around our oxygen, so we know that that's right. We have these lone pair electrons, these ones over here, and we have these bonding pair electrons drawn as straight lines. There's 2 electrons in there. Sodium fluoride, on the other hand, is an ion, so we draw it with these square boxes, usually square brackets, usually used to denote concentration, but in this case, square brackets. So there are no electrons in the valence shell of this sodium because it's moved over here. You can see it right there. So we've got a little plus up here to show that it's a positive ion. Here we have 1 valence electron from sodium and 1, 2, 3, 4, 5, 6, 7. It's in group 7. Valence electrons from fluorine, which gives it a minus because it's got 1 extra one there. And that's how we draw those. Lewis structures for organics and covalents. Covalents and ionics. All right, question 17. Copper catalyzes the reaction between zinc and dilute sulfuric acid. Zinc, so I should have put that on the next line. Zinc solid plus sulfuric acid goes to zinc sulfate plus hydrogen gas. Outline how copper affects. So an outline is less detailed than an explanation. So we state 1 mark for saying copper provides an alternative pathway to lower the activation energy, and then you could say that copper is not consumed in the reaction, and that's how copper affects the reaction. Provides an alternative pathway to lower the activation energy. So there's no real detail there, but it's like, this is what happens, and this is why it can do it. It's still there at the end. That's why it's not up there. Okay, sketch on the diagram the impact of adding a catalyst. First off, it moves the activation energy, that's EA here, to the left, and we need to show that more molecules are reacting, right? So we just draw it there. That's all it is, to the left. It's a sketch, so you don't have to measure anything, and you won't have to measure anything with these Maxwell-Boltzmann diagrams, because it's not a two-scale diagram. Sketch on the diagram the impact of increasing the temperature. The peak here is what's going to move. It's going to move to the right, and this will also move more molecules above the activation energy. But what it's saying is that the average energy of the molecular particles should be around here. Majority of particles should be about there. Almost nailed it. And so there's that, right? So there's our activation energy. I've just extended that further up so it's clear. And we can see that we have a bigger proportion of our molecules are reacting over here. All right, moving myself over here. There's a much quicker question. Explain the impact of the rate of reaction of grinding the zinc from large pieces into a powder or increasing the concentration. This gives our students a chance to show what they know. The IB would probably not be as forgiving. It would give you 1, not 2. So, first up, grinding increases the surface area, therefore more collisions occur. This increases the rate of reaction. Magic, right? Explain what happens, why it happens. You've also named it in here, but it wasn't part of the question, so there's no marks for that. Or alternatively, increased concentration, therefore more particles per unit of volume, therefore more frequent collisions. Okay, so increased concentration gives you more particles per unit of volume, therefore more frequent collisions. You could also write more frequent collisions in the correct orientation. You probably should, to be honest, but I accepted that one there. Okay, so a calculation question. Fun times. So if 9.36 grams of zinc metal reacts with H2SO4 in the equation in part A above and it goes to completion, in other words, there's more than enough sulfuric acid, calculate the volume of H2 gas produced. 2 marks. Alrighty, first we get 1 mark for correctly calculating the moles of zinc and the 1-to-1 moles of H2. So really you're getting marks for calculating the correct calculation of hydrogen gas. You then get 1 for the correct use of molar volume to calculate H2 volume. Okay, so let's have a look, see how this is done. So first, we look at how many moles of zinc we have, right? We've got every equation up here. All right, that all works. So mass divided by molar mass, so 9.36 grams divided by 65.38 gives us 0.1432. We do not ever round down in your working. That is your final answer. There's no rounding before we do that. So we have 0.1432 moles of zinc. There's a 1-to-1 ratio there, so therefore we have 0.1432 moles of hydrogen gas. Let's calculate the volume. So moles equals volume divided by molar volume. We rearrange that to give us our volume equals moles times molar volume. So we go 0.1432 times 22.7 litres, or decimeters cubed. This gives us 3.25 decimeters cubed. That's our volume. So 1 mark for there, 1 mark for there. Before we do move on, I always tell my students to write, I haven't done it here, but I always tell my students to write an answer statement. So they would then have that done and see how that's the correct significant figures. So they would write 3.25 decimeters cubed of hydrogen gas is produced in the reaction of zinc and H2SO4. That's how I would get them to finish that question off. You know, that way sort of a very clear answer, the marker knows exactly where it is. They're going to find it anyway, they're not silly, but just minimize any variability there. Fun energy calculations. So in the aqueous solution, potassium hydroxide, that's this bad boy, and hydrochloric acid, that's this one, react as follows. The data below is from an experiment to determine the enthalpy change of this reaction. So we have 50 centimeters of 50 centimeters cubed, or 50 milliliters, of 0.500 moles per liter, or moles per decimeter cubed. Solution of potassium hydroxide was mixed rapidly in a glass beaker with 50 centimeters cubed of 0.500 moles per decimeter cubed solution of HCl. The initial temperature is 19.6. Final temperature is 23.1. State with a reason whether the reaction is exothermic or endothermic. It is exothermic. And, so you got to have both. That's not an answer end. So it's exothermic due to the system's temperature increase. You are given this data here. Refer to it. Okay? Refer to it in your answers. So, we want to calculate the enthalpy change of this reaction in kilojoules per mole. Kilojoules is important. You'll have to make a conversion there. Assume that the specific heat capacity of the solution is the same as that of water. We get that out of our data booklets. So, you get 1 mark for the correct calculation of heat released, 1 for correct per mole, so that's your enthalpy, with the appropriate sign. Alrighty, so here are our possible equations. We have Q equals MCAT, my favorite equation in all of chemistry. Actually, no, it's this one. Delta H equals MCAT over moles, negative MCAT. We have delta H equals negative Q over N. We have concentration equals moles per volume. Moles equals concentration times volume. So let's have a look. All right, we are going to use these two because these are the variables we have, right? Like that makes sense. Oh, these three, sorry. I could tell there were three there. I just couldn't count. Here are our variables. I always get everyone to write down their variables. I think it just makes your life so much easier. You have room. Here you write bigger because you're writing on the screen. But you have room to do this. So Q equals, we don't know. Delta H equals, we don't know. Moles, we don't know. But when we write Q, we know we've got mass. We've got C, this is the value we look up. Specific heat capacity of water. Delta T, we can calculate that real quick. So that's 23.1 minus 19.6. So what's the change there? How much has it gone up by? 3.5 degrees Celsius. Get that out of here. 3.5 Kelvin. Then we have moles. We don't know that. But we do know the concentration and we do know the volume. Now remember, we're just looking for one of them. Really important, the volume here is going to be in litres or decimeters cubed. So we need to move from this centimeters cubed to litres or decimeters cubed. So that means dividing it by 1,000. So you get 0.0500 decimeters cubed. So Q equals MCAT. Love it. That's 100 grams times 4.18 joules per gram per Kelvin times 3.5 Kelvin. Just to show you where we end up, we cancel out the grams. They cancel out. The kelvins cancel out. We're just going to get to joules because that's what heat is. So we have 1,463 joules, not kilojoules, joules. So that is the heat released. Okay. Now, that's it in kilojoules, 1.463. To get joules to kilojoules, you divide by 1,000. So now let's do some MCATs. Let's work out our delta H. So we need to know how many moles we have of the thing we're interested in. In this case, we'll look at sodium hydroxide, I believe, potassium hydroxide. So we have concentration times volume. So we've got, this is our concentration, 0.500 times 0.500. Note here that volume is, I've written volume as dm negative 3. It should say moles per decimeters to the negative cubed. Decimeters cubed, straight cubed. Should say that. I made a mistake there. So we cross out that. They cancel out. If it wasn't decimeters, if it was decimeters negative cubed, they wouldn't cancel out. But they do cancel out, which gives us 0.0250 moles. Okay. And now we just put these into this equation here. So delta H equals negative Q divided by moles. So we have our specific heat, our heat released up here, negative heat released divided by how many moles, which gives us an enthalpy change of negative 58.5 kilojoules per mole. Good question. Extended short answer questions, and we'll see how we go. All right, let's keep going. All right, so we have a Haber process question. This process is something I think probably every chemistry student could recite backwards, by the time they're in year 2 of the IB DP or the end of the HSC in Australia. Like, I think you know this. What you see it all the time, and it's because it's a really important, and it's popped up a few times in this exam because we sort of wanted to reinforce the importance of this equation and kind of having it backwards. So knowing it backwards, I mean. So what you end up with is 1 nitrogen molecule plus 3 hydrogen molecules goes towards 2 ammonia molecules, but it is an equilibrium. Everything's a gas. Delta H is negative, so it's exothermic. We're going to use the information given here to state and explain the effect on the yield of the ammonia increasing. That means you need to refer to what's happening up here. So we're talking about yield, not rate of reaction. That's a really common place for those mistakes to happen. So if we're looking at pressure, right, we want to focus on the amounts of each molecule of gas there are. So there's like 4 molecules on this side, 2 molecules on that side. So it's going to increase the yield. Okay, so that's stating the effect. And it's because there are fewer moles of gas on the left-hand side, and equilibrium will drive it to the right-hand side to make up for those. We've sort of shortened this down. So links to fewer moles of gas and equilibrium. So we're going to talk about those two things. With temperature, we want to talk about the delta H is negative, right? So this is going to decrease the yield, and we want to relate that to the exothermic nature and the equilibrium shift. So you'd say something along the lines of, as the system is exothermic, an increase of the temperature, the system will try and reduce that, therefore driving it to the endothermic side to the left, decreasing the yield. All right, equilibrium constant expression, Kc. We often refer to these as the porks because they, it's K equals products over reactants, and then you got the concentration in there as well. So here we have Kc equals products over reactants. These square brackets refer to concentration, and then of course we put any coefficients at the side here. So Kc in this case equals ammonia, concentration of ammonia squared, divided by the concentration of nitrogen times the concentration of hydrogen cubed. And that's the Kc expression. So when we talk about the Haber process, we don't actually run it at like its best potential. Yeah, like we're not like sort of running it in the way where we get the most yield possible. We sort of have to moderate the conditions and monitor the conditions. So it runs at a temperature of like 500 degrees Celsius and a pressure of 200 atmospheres. That's big pressure, but it's not the biggest pressure, and that's only a moderate heat, moderate temperature. So why do we use these instead of those that give the highest yield? So we want to focus on those temperatures. Lower temp gives a higher yield but a lower rate. So we get one for talking about how like we use a lower temperature because we get a higher yield, but it's really, really slow. So we have to have that moderate temperature. We use a high pressure, gives a high yield, but it's dangerous and costly. Yeah, so we can't just run it at the lowest possible temperature, high yield but too slow. We can't run it at the highest pressure because it's dangerous and expensive. So here we have an HL question. The initial rate of reaction was determined for the reaction between bromide ions and bromate ions in the acidic solution. Just here, it's a little bit so some redox stuff in there. This is an interesting question. I really enjoyed this one. So 4 trials were carried out, the results given below. But what? Magic. Okay, I like these. We're always looking for ones where they keep them constant. So that becomes your constant variable, and this one will become your independent variable, and so on. I'm just going to move myself over here. Okay, so our question has us deducing the overall rate equation. We have our 3, what are they called? Reactants right here, and we can do some fun stuff. Okay, so you get 1 mark for the correct method and 1 for having the correct orders of reaction. Okay, so, there's like challenges there. All right, so if we look at bromate, if we keep bromide constant and we keep the hydrogen constant, and we double this equation, but we see that the initial rate, double this concentration, we see that the rate doubles, okay, that makes it first order equation. So when we're looking at bromide, from here to here, right? We're keeping the bromate constant, and we're keeping the hydrogen constant. So here it doubles, and here our rate also doubles. Therefore, it's also first order. Okay, so we've got first order here, first order here. Let's have a look at the hydrogen ions. So here we double, okay, but here it doesn't double. It's multiplied by 4, which is 2 squared. Okay, so this is multiplied by 2 to the power of 1, 2 to the power of 1, which is 2. Here it's multiplied by 2 to the power of 2 to get your initial rate change. Okay, that makes it a second order. So rate equals K, got to have that K. Bromate, bromine, or bromide, sorry, H hydrogen ions squared. So that's our rate of reaction. Okay, so the rate of reaction at 50 degrees Celsius is 3 times the rate at 25 degrees. Calculate the activation energy in kilojoules per mole. This is a hard question. There's a lot going on here. Well, it's not a hard question. It's just it's using an equation that you don't use it a lot. So it's a tricky one. So for this reaction, use sections 1 and 2 of the data booklet. All right, you get 1 for substitution. So you're going to find the right equations and substitute the right answers here. And then you get 1 for the correct answers. Okay, this is the equation from the data booklet. Natural log of K1 divided by K2. Activation energy over the real gas constant multiplied by the reciprocal of temperature 2 and the reciprocal of temperature 1. Okay, so let's start substituting, right? This is a K1, 1, K2 is 3, because it's like 3 times, right? So you can just go, treat that as 1, treat that as 3. That's a nice little number. Real gas constant is 8.31 joules per moles per Kelvin. Temperature 1 is 298 Kelvin. Temperature 2 is 223 Kelvin. It's important that we use kelvins for this because it's Kelvin here. So then we sub them in, right? Natural log 3 over 1, that's going to be 3, equals negative EA divided by 8.31 times times the reciprocal of 323 minus 298, and then it becomes ln 3, that over the top there, times that, and we're just sort of working through it each step, right? So natural log of 3 is 1.098. This is the equation done here, and see, I like to sort of do each of these each step. So it then becomes EA times this divided by that, okay, because that's a negative number, but boom, they cancel each other out. Well, the signs cancel each other out. And we end up with activation energy equaling 1.0986 divided times 8.31 divided by 0.00260. We end up there with 35,110 joules per mole, which is obviously 35.1 kilojoules per mole. All right, some more HL time. Hydrogen is manufactured from methane by a process called steam reforming. Here we have methane plus water vapor goes to carbon monoxide gas plus 3 hydrogen molecules. It is an endothermic process. Enthalpy is plus 206 kilojoules per mole. Deduce the equilibrium constant. See, there's a trick here. What they're actually asking you, because you've already done the equilibrium constant earlier, is do you understand that this is a gas, not liquid, therefore it's in Kc? That's what this question is testing you. So it's really sort of pushing hard to how well you understand equilibrium constants. Therefore, just like before, if we're including it, it becomes concentration of methane, concentration of water vapor under the concentration of carbon monoxide and the hydrogen cubed. So the reactants are sort of passed over nickel metal. Following mechanism is proposed. And we have our slow step here. Deduce giving a reason the role of nickel. Okay, so we see nickel's here at the beginning. It's here at the end. That's a strong clue. It's a catalyst and it's not consumed. That's the reason, right? It's not consumed or it's regenerated. Alright, calculate the standard entropy change, delta S, of the forward reaction in joules per Kelvin. There's a 1 mark for this. We use section 13 of the data booklet, and the standard entropy of hydrogen is given there. That means it's not in the data booklet, right? So they give it to you. Okay, so let's have a look. First off, here's our equation for calculating standard entropy. Change in entropy, it's the delta sum of the entropy of the products minus the sum of the entropy of the reactants. Okay, so we can write sum of the delta entropy equals the sum of the entropy of carbon monoxide plus 3 times the entropy of hydrogen, because we've got to keep those ratios in line, minus the entropy of methane plus the entropy of water vapor. And then we just substitute in our answers. Just like this. Comes 214.6 joules per Kelvin. I would probably make that 215, to be honest, given that we have 3 significant figures up there. So I'm going to shift over here. Yoink. Okay, so calculate the Gibbs free energy, delta G, of the equilibrium constant, Kc, for the forward reaction, 1500 Kelvin, using sections 1 and 2 of the data booklet. That's where the equations come from and the information. If you're unable to obtain an answer for part C, use this, but it's not the correct value. So in other words, if you couldn't do this, use this one. Other courses where there's carryover stuff will use, you'll have to come up with an answer from there to bring into there. I like that about the IB. They give you an answer to use if there's carryover stuff. We still treat it as carryover, by the way, if you make a mistake there, whatever. But if you can't get an answer at all there, you've got something to go on with. Alrighty, so Gibbs free energy, Kc. Those are our points where marks come from. 1 mark for working out Gibbs free energy, 1 for working out what the equilibrium constant is. These are the equations we're going to use, or we could use, right? So we've got delta G equals delta H minus T times delta S. We have delta G equals negative RT link Kc there, natural log of Kc. Or we have Kc equal, that's just this one rearranged, equals E to the power of minus delta G divided by RT, right? And you'll notice that this is the one that has all the information we need. So let's do it. Alrighty, so delta G, delta H, delta S, off we go, plus 1500 Kelvin. We're also going to use this one as well to get delta G. There's the real gas constant. Okay, so this one here, we've got to make sure we convert that to joules per mole, because that's what entropy works in. Alright, so delta G equals delta H minus T divided by times delta S. So we just substitute in our values. This, and we need to convert it. There we go. And then we'll have to unconvert it in a minute. So we've got this equation. We rearrange it, right? Natural log of K gives us this one. And then we just substitute our values in. Off we go. Remember, we've already converted back, because you want to run in this in your equations, but that's the way we give answers. There we go, and the natural log Kc equals 9.3, therefore Kc equals 1.1 times 10 to the power of 4, which also means that that equation lies quite far to the right. Alright, I hope that was helpful in going through that paper and any questions that you have. Remember, a version of that paper will be in the link below. I'll just put the HL version in, and if you knock out questions 21 and 22, as well as in the second half of the paper, and in paper part 1, 16 to 25, that'll get rid of the HL questions out of there. I hope that made a lot of sense. If you have any questions, any errors you found, get back to me and we'll fix them up. Or I'll put in a call out telling you where the errors are. Okay, thanks very much. I'll see you next time. Bye now.